You ask your phone for the weather, and somehow it just gets it. Your email zaps junk mail before you even see it. How does it do that? Well, it's not magic, and it's not just a simple line of code. It's a really deep process of digital learning. And today, we're going to pull back that curtain and see exactly how a machine learns.
But that raises the big question, doesn't it? We throw that word learn around all the time when we talk about AI. But is it really learning the same way we do, or is it something else entirely? To get to the bottom of that, we first need to understand where this all came from.
All right, so to really get what machine learning is, we first have to talk about what it's not. You see, there's a huge difference between an AI that just follows a set of orders and one that can actually, learn. It's really a tale of two very different kinds of AI.
So on one side, you've got what's called rules-based AI. The perfect example is your thermostat. It follows one simple programmed rule. If the temperature drops below, say, 68 degrees, then kick on the heat. It's useful, for sure, but it can't learn anything new. But then, you've got machine learning. Think about your spam filter. Nobody sat down and wrote a rule for every single possible spam email in the universe. No way. Instead, developers showed it millions of examples of emails, and from that data, it learned the patterns. It figured out the subtle clues of what makes an email junk. It learns from the data itself, not from a list of commands.
Okay, so if not just a bunch of if-then rules, what's actually going on under the hood? How does this new kind of learning even work? Well, let's peel back the layers and take a look inside this new kind of digital mind.
At the very heart of it all is something called a neural network. And yeah, it's a system of interconnected digital neurons that's kind of inspired by the structure of our own brains. Each connection between these neurons has a weight. You can think of it like a little volume knob that controls how much influence one neuron has over the next one. And the entire incredible process of learning is really just the act of fine-tuning millions of these tiny knobs until the network starts giving you the right answer.
And this is basically how it happens. It's like a four-step dance that just repeats. First, you feed it some data. Second, the network takes a guess. It makes a prediction. Third, it calculates how wrong it was, its error. And fourth, and this is the real magic right here, it uses that error to work its way backward through the entire network, just slightly tweaking every single one of those little knobs to be a little less wrong next time. That's called backpropagation. And it does this over and over, millions of times, getting just a tiny bit smarter with every single pass.
Now, the most common way to get these networks up and running is to give them a guide, a sort of digital teacher that basically has the answer key to the test.
You see, machine learning isn't just one thing. It's more like a big family of different strategies. You've got these three main branches: supervised, unsupervised, and reinforcement learning. And we're going to start with the big one, the one that powers a ton of the AI tools you probably use every day: supervised learning.
Supervised learning. The name pretty much gives it away. The AI is supervised, and its supervisor is the data itself. You give it a massive data set where every single piece of information is already labeled with the correct answer. So a picture of a dog is labeled dog. A sketchy email is labeled spam. It's exactly like giving a student a giant box of flashcards with the answers already printed on the back. And the process itself is actually pretty straightforward. You take all that labeled data and you split it into two piles. You use the bigger pile, the trained data, to teach the model. Then you use the smaller pile, the test data, to quiz it on stuff it's never seen before. Because here's the key. The goal isn't just to memorize the training set. The goal is to learn the underlying patterns well enough to make good predictions on brand new data.
If you want a really simple way to picture this, think about an algorithm called a decision tree. It literally works just like the game 20 Questions. The algorithm learns to ask the most efficient series of yes or no questions to split all the possibilities and back its way into the right answer. Is it an animal? Does it live in the water? It's just like that, but for data.
Okay, that's all well and good when you have a perfect answer key. But what happens when you don't? What if all you have is a giant, messy, unlabeled pile of data and you just tell the AI, good luck, figure it out? Well, that brings us to autonomous learning. This is unsupervised learning. In this case, the AI gets a massive dump of data with zero labels, no instructions, no answers. Its job is to dive into that chaos and find the hidden structures all on its own. It's basically being a detective, looking for clues and connections that nobody told it to look for and grouping similar things together. A fantastic analogy for this is packing a suitcase, right? You've got this huge pile of stuff on your bed, but your bag can only hold so much. You have to figure out what's most important, your principal components.
You fold some things up to make them smaller, and you leave the less important stuff behind. Well, that's kind of what these algorithms do. They find ways to condense complex data down to its most important features, which makes it way easier to handle.
And finally, we get to the third major approach, reinforcement learning. This one is all about learning by doing, pure trial and error. Just imagine an AI agent learning to play a video game. It has no instruction manual, it just starts mashing buttons. When it finds a coin, it gets a reward point. When it runs into a monster, it gets a penalty. After millions and millions of tries, it starts to figure out strategies to maximize its score, strategies no human ever taught it. This is how AIs learn to master incredibly complex games.
So, we've got the methods, we've got the digital brain, but you might be asking yourself, these ideas have been around for a while. Why is AI suddenly exploding right now? Well, it really came down to a perfect storm of two key ingredients.
Ingredient number 1, data. And I don't mean just a little bit of data. I mean mind-boggling, astronomical amounts of it. The internet basically became this planet-sized library for AIs to read. You see, these deep neural networks are incredibly hungry for data, and for the first time in history, we finally had enough raw material, all the text, all the images, all the videos, to actually feed them. And the second ingredient, pure raw horsepower. And the funny thing is, it came from a totally unexpected place. Video games. Graphics processing units, or GPUs, were built to do one thing really well: perform thousands of simple calculations all at the same time to render amazing graphics. Well, it turns out that kind of parallel computing is exactly what you need to train these giant neural networks. The GPU basically became the engine of the entire AI revolution.
So, we've dug deep into how a machine learns. We've seen the process. But now we have to circle all the way back to that very first question we asked at the beginning. What is it that's doing the learning? Is what's being built here a mind?
And this brings us to what might be the most crucial distinction of all. This quote just nails it. The computational model thinks, but does not understand. An AI is an absolute master of finding patterns in data on a scale we can barely imagine. But does it actually grasp the meaning behind those patterns? Well, that is the central debate.
And this debate really leads us down two completely different paths for the future of AI. On one side, you have the computational theory. This is the idea that a mind is basically just really sophisticated software, and it doesn't matter if that software runs on brain cells or on a silicon chip. But on the other side, there's the embodied cognition theory. This idea argues that a mind can't just exist in a digital box. It says that real intelligence needs a body to interact with the world, to feel things, to move, to actually experience reality. And when you think about it that way, it really highlights what makes our own learning so, well, human. For us, learning isn't just about crunching data. It's all wrapped up in our own subjective experiences, our emotions, our physical interactions with the world around us, and of course, that most mysterious thing of all, consciousness. These are the parts of intelligence that, so far, machines haven't even begun to touch. And that leaves us with one final fascinating thought. This whole incredible quest to build an artificial mind is forcing us to stare back at our own. By trying to define the limits of what a machine can do, we're also, maybe for the very first time, starting to map the unique, amazing landscape of our own intelligence. In building this mind in the mirror, we might just end up understanding ourselves a little bit better.